Mhm.
Hello, everyone. Come on in. If you have any questions, go ahead and ask them. Have to start class pretty soon, but I can afford some time for questions. Anyone? All right. So last time I was showing you applications of Newton's second law. Thank you, Infinity. I was showing you applications of Newton's second law. Specifically, I had shown you how to deal with inclined planes. I showed you how to deal with that fuzzy dice type problem, which mainly was about a different way of solving systems of equations. So you are supposed to have, of course, various tools in your tool bag for solving systems of equations. That's one that you probably didn't get from your high school algebra 1 or 2 or pre-calculus teacher, just because the way math works is it's highly unlikely that you want to necessarily suggest to a student that you divide one equation by another. But in physical problems, that's a little bit different. So we did that. Uh, I did an Atwood machine, and now I'm going to do an Atwood machine on an incline. But this time, instead of doing it with numbers, I'm going to go ahead and do it with symbols. Then I'm going to do an apparent weight problem. And from there, I'm going to motivate some of the stuff for chapter 5. So we're essentially, I've given you enough to really do chapter 4 already. So that's why your homework will be due this Sunday. You also have, of course, an online test that's due Sunday. So make sure you get that knocked out as well. But the main thing is you will have chapter 4 due this Sunday. And in principle, chapter 5 could be due as late as Wednesday. But I will likely move it on to the following Sunday, but I'm not sure of that yet. So trust the dates for right now, and just be advised that you need to start on chapter 5 as soon as you finish chapter 20, chapter 4. So does anyone have any questions? I do see that some students are going ahead and type in their name for the roll sheet. That would be helpful for me. I usually ask for a little later in the class, but it doesn't matter too much. I'm not really trying to see whether you're coming and staying. I'm more about whether you showed up at all. So that's fine. So no questions? All right, well, let me start off with this inclined plane problem where I'm going to be doing an Atwood machine, but it's on an inclined plane and it is frictionless, and the pulley is massless and frictionless as well. So it's a simplification, but it's a simplification that will come in handy because we know exactly what we got with the Atwood machine. And when we do something that's like the Atwood machine, in some sense, there should be some variable we can change to make the new problem like the old problem, or some variable we can change with the old problem to make it like the new problem. And if they don't agree about the answers, then that's a good indicator that we didn't do it correctly. So let me start by sharing my screen. And I'm going to go ahead and admit those two people. And now sharing process is trying to happen. Just waiting for it to pop up any old second now. Okay, that's popped up. That's good. I'm going to pop the chat up too so I can see if anybody tries to answer any of my questions. I've got that. So this is going to be an Atwood on an incline. So let's say inclined Atwood machine, no friction. So what I'm going to do is I'm going to draw an inclined plane like so. I'm going to say this angle right here is phi or phi. I'm going to put a pulley there. This is a massless, frictionless pulley. Now, in addition to that, I am going to have a mass little m. And notice that string is essentially parallel to the incline. That's important. Let's actually undo that. Now it's more correct. And then I'm going to have a very big mass, capital N, hanging from that side, a capital M hanging from that side. So this is our Atwood machine. What I would like to know is the acceleration and the tension. So I've explained to you guys before, but the fact that the pulley is massless and frictionless tells us that there should be no reason that the tension on the big M is any different from the tension on the little m. If in fact the pulley had mass and or friction, then the pulley or the tension on the right hand side attached to the big M, that tension would be responsible for accelerating the mass little m up the incline. But it would also be in addition to that, responsible for overcoming the friction between the pulley and the axle, and also for accelerating the pulley, which has a mass. So when the pulley is massless and frictionless, we don't have to deal with that. I'm going to start by drawing a free body diagram for little m. And what often happens is it's smarter to actually choose a coordinate axis that is parallel to the incline, like so. When I do that, what I have is a mass here of little m that has a weight mg acting on it. I want to let you guys recall that if that's the incline, then this angle right here is the angle that we called phi or phi. Okay, I do think it's technically pronounced phi in Greek. If anybody's Greek, please let me know to be sure. I think I asked my friend who's from Cyprus, and she once told me it was phi. The main thing to realize is right now you can see that if I continued this dashed line up to here and then went up that way, see the blue lines I just put, we'd realize that that's a right triangle, and that means this angle is 90 minus phi. Okay. But we'd also notice that this angle right here is also 90. So this angle right here would be 90 minus parentheses 90 minus phi. And I think you can see that that turns out to be just phi. Okay. So with all of that in mind, I think you can all see that we can now break this weight vector up into a component that's parallel to the y-axis and a component that's parallel to the x-axis. So I am going to do that now. I am going to choose red as my negative direction. So that right there is the weight sub y. And then this right here is the weight sub x. And I think from trigonometry, you can see that the weight sub x would be mg sine phi, and the weight sub y would be mg cosine phi. Everybody agree with that? Does that seem reasonable to everyone? Whoa. Okay, now in addition to that force acting, we have a positive force acting, which I'm going to use for green. That positive force is the tension in the rope. I'm going to call that T. And also the normal force from the incline, I'm going to call that N. Now, in this case, since we're not dealing with friction, we don't necessarily need to know exactly what N is, but still I show it there for completeness. Now I'm going to write the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Notice that as the rope pulls the lowercase m up the incline, we don't expect the little lowercase m to be bouncing up and down. In fact, the velocity parallel or anti-parallel to the y-axis should be 0. And if you wait a couple seconds, it's going to be 0 again. If you wait a couple seconds, it's going to be 0 again. That means the acceleration, in fact, is 0. So in this case, all we get is n, which points in the positive direction. So I'm going to call that positive n. And then mg cosine theta, or cosine phi, which points in the negative direction. Now, remember Newton's second law says the sum of all the forces, not the subtraction. But because we are working with the components and the components can have plus or minus signs to indicate their direction, I'm not going to take the time to write plus and then a negative number. I'm just going to say minus mg cosine phi. That's all the forces acting because there's no friction, and all that has to equal 0. So we get equation 1. Evidently, the normal force is just equal to mg cosine phi. But again, we don't need that. So I just did it for completeness. Similarly, the summation forces in the x direction is equal to mass times acceleration in the x direction. Now, if I were to pull the big mass, big M, downward 1 inch in 1 second, then the little mass, lowercase m, would move up the incline 1 inch in 1 second. That shows you that their displacement's the same, 1 inch, 1 inch. It also shows you that their speed is the same, 1 inch per second to 1 inch per second. Now, if I pulled the big M down 1 inch in 1 second, and then in the next second I pulled it down 2 inches, I would see that the lowercase m would go up the incline 1 inch in the first second, and then it would go up the incline 2 more inches in the second second. So now I see that the accelerations are the same, and we're going to call that acceleration just plain a because it's the only one that exists. Okay? So the summation of forces in the x direction gives me t that's positive. So I'm going to say t minus, in this case, it's mg sine phi, and all that is equal to ma, and I'm going to call that equation 2. Okay? Now, I've made going up the incline the positive direction. Now, if we followed that up the incline around the pulley, it would start going down towards M. So what we'd see is that when big M goes down, that's the same as little m going up the incline. So I'm going to treat downward for big M as the positive x direction. So here's my coordinate axes. That's positive x. I'm going to say this is the mass big M. And I am going to say that this vector right here is the weight. And if you were in that box, which might be an elevator car or a plexiglass box or whatever, what you would say is, wow, I really feel like in this plexiglass box that I would fall at 9.8 meters per second every second. But luckily that rope is slowing me down. And that's what tells me the tension in the rope will be in the upward direction. And that's the negative direction. And I'll call that T. Now, in principle, I could have drawn that over to the left, so that's what I'm going to do now. Okay, evidently I'm not going to do that. Let's try it again. Now I'm going to try to paste it. Now I'm going to move it over to here. So that looks pretty good. All right, now I've got just one direction to deal with the forces in, and that's in the x direction. So the summation of the forces in the x direction is equal to mass times acceleration. Again, we have no reason to subscript the a. In this case, though, what we get is big mg minus t is equal to big ma. And that's going to be equation 3. Okay. So this is our system of equations. Equation 1's not necessary, but we do have now the equation for the normal force. What we also noticed last time was that, in algebra, like in pre-calculus or in algebra 1 and 2, when you had systems of equations, sometimes you would multiply one equation by, say, 2 and the other equation by, say, -3. And what that would do is possibly take a 3x and make that -6x, and take a 2x and make that +6x, and then you could add the +6x and the -6x and they'd cancel out. Well, we already have that set up here with the t. So I'm going to say add equations 2 and 3. And what's going to happen is I'm going to get mg minus t. Now I'm going plus equation 2, which would be t plus t minus lowercase mg. All that's equal to little ma plus big Ma, which obviously has a common term of a. So I'm going to factor out that, or a common factor of a. So I'm going to factor out that a and just call this m plus little m times a. Looks like someone else came in. So everybody follow what I did there? Notice the t and the negative t cancel out. And in fact, I'm in a good place to actually solve for a. Before I do that, though, I want to remind you that for the Atwood machine, what we got was a was equal to m minus m over m plus m, all that times g. And what we got for t was 2m over m plus m times lowercase mg. So that's what we got for the Atwood machine. And that's going to be something we can use to make us make sense of the answer we get. So if I go ahead and solve for a now, I think you can see that I get a is equal to, oh, anybody see what I left off when I added equation 2? I got so excited I didn't even write it. So I'm going to do that. I'm going to try to establish that little green line again. And now I'm going to try to scoot this down. Okay, that was super helpful. I like the way it just disappeared there on me. I'm going to say cut. And now I'm going to say paste. And I'm pasting it down here just a little bit so I have enough room. So now what I'm missing, remember, I actually had everything. I was supposed to say t minus mg sine phi. So I have left a mg sine phi. And again, the other part that I jumped to, and probably is the reason that I ended up leaving off the sine phi, is big M plus little m with a factored out. Now I can say that m minus m sine phi divided by m plus m, all that times g, is what my acceleration is. Now, this Atwood machine, remember, was essentially a pulley with a mass and another mass, right? So what angle would I have to make this incline to make little m look more like the Atwood machine? I'll ask you more pointedly. Would the angle phi be 0 if I wanted this inclined plane Atwood machine to look like the regular Atwood machine? Or would it be a different angle? Anyone? I don't see any chats coming up either for their answers. Whoa. If I really wanted to make this like the Atwood machine, what I would want to do is make that angle phi equal to 90 degrees. If I did that, then I think you see A would become m minus m times the sine of 90 degrees over m plus m, all that times g. But what is the sine of 90? Anyone?
1.
1. So you end up getting m minus m over m plus m, which is exactly what we got for the Atwood machine, right? So that's a nice check. And that's one of the things we do in science is every avenue we have to check our predictions, our theory, our hypothesis, or whatever, we try to use that. For example, most recently, we finally launched the James Webb Space Telescope. And I was so excited to hear this because I could use it in my classes. Specifically, the head of the science mission for the James Webb Space Telescope, when asked, "What are you going to look at first?" she said, "The first thing we're going to do is work out our distance ladder and make sure we're all correct about that." So, over time in astronomy, we've had to make some really weird approximations to get an idea how far away things are from us in space. And measuring the distance to a thing is about the hardest thing we can do in astronomy. We can use laser sighting and echoes and stuff like that to find the distance between the sun and the earth, or the moon and the earth, and pretty much basically all the planets with respect to the distance to the sun. Once we get further than that, then the next closest star is about 4.2 light years away. We can use parallax to get that and maybe go up a power of 10, maybe even close to a power of 100 above that. But once we get out of there, there's nothing else we can do from a parallax standpoint. It's just too small of a difference in directions when we go to try to use parallax. So we had to go to other things. Well, one of the things we did, and this is kind of absurd, but one of the things you might do is you say, okay, well, let's look at our galaxy and let's look at a globular cluster, which is a type of star formation. And let's say, let's see what the diameter of the largest globular cluster is around our galaxy and around any other galaxies that we can see. and measure. And when we did that, let's say it came up to be that the largest globular cluster we found around any galaxy that we could measure was in fact about 25 light years. So then what we might do is if we're looking at a distant galaxy that we can't measure the distance to, if we see a big globular cluster, we might make the assumption that the diameter of that globular cluster is 25 light years, and then use that to determine the distance to it. Okay. Now, that's based somewhat on the Copernican principle, which basically the Copernican revolution said that we are not necessarily special in this part of the universe. What I mean by that is we do not expect to go to another part of the universe and find that the laws of physics are different. In fact, we also suspect that if I look off straight across the street here in space for any distance, I expect it to look exactly the same as if I flew off at that 45-degree angle above horizon and 45 degrees east of north. I would expect to find the exact same stuff in that direction, and so on and so forth. So we expect the largest globular cluster around our neighborhood to be about as big as the largest globular cluster around any neighborhood, and that allows us to do that. When we get a new technology like the Webb Space Telescope, the first thing that she wanted to do was actually point it at the things we already know about, but using this greater technology, see if we were right and make sure that all that science we've been using in the past is still valid. So that's what we're doing here is we're actually looking at a new solution to a problem and comparing it to the existing solution. Of course, this is all sorted out physics, so this isn't that big a deal. But when you're a student and you're going through learning how to solve physics problems, this is excellent. This keeps your brain content. It keeps your brain thinking in terms of experiment. It keeps your brain thinking in terms of how do I let one experiment look more like another, so on and so forth. So now that I have that, I got to also solve for the tension. I'm going to use equation 2. So I'm going to say from equation 2, I'm going to get that T is actually equal to M times A. Actually, let me write, I'm going to pull the mg sine phi over to the right first. That's going to become positive. So I'm going to say mg sine phi, and then that's plus MA. So I've got a common factor of M in there. So I'm going to use that. Let me also break this up so we don't get confused what part's what. I'm going to go over here and say this is now T, and I'm going to factor out the factor of M. I'm going to put a big square bracket there. And this first term is going to be G times the sine of phi. And this other term is just going to be the acceleration we just found, which was M minus lowercase m sine phi. And I'll try to make that a little more obvious. Okay, clearly I made it worse. So that was great. I love it when that happens. Okay, m minus m sine phi over m plus m. And then, of course, all that's times G. Okay, now I have a common factor of mg, so I'm going to pull that out. And I'm also going to get a common denominator. That common denominator is going to be m plus m. Okay. Now, when I do this, I have to take the g sine theta and multiply it by m plus m. So I'm going to get m g, and I'm sorry, I said theta again. Big M g sine phi plus little m. Oh, actually, I don't need the g. Let me get rid of that because I forgot I pulled the g out already. So now I'm going to say big M times the sine of phi plus little m times the sine of phi. And now I have to do the, there I go again. Keep trying to make that phi clear and I end up making it actually worse. Okay. Now I've got to do the same thing, but notice there's a plus sign in front of the m minus m sine phi. If there was some other symbol in there, like an m or something like that, I got to keep in my mind that the fraction bar is the same as parentheses, so you'd have to distribute. In this case, it doesn't matter, so I look out. So the first thing is just going to be plus m, and then the second thing is going to be minus m sine phi, like that. So you can see that the m sine phi negative cancels out with the m sine phi positive, and what we ultimately get is that t is actually equal to m times 1 plus the sine of phi, all that divided by m plus lowercase m, and then all that multiplied by mg. So that's the tension in the rope for this inclined plane Atwood machine. Again, remember the Atwood machine, that means phi equals 90 degrees. And when phi is equal to 90 degrees, t becomes m times 1 plus 1 over m plus m times mg, which is in fact 2m over m plus m times mg. So again, we get another check mark. Everybody follow that? Any questions on that one? Okay, so there's another problem I want to show you, and this is related to apparent weight. So for instance, if you're in an elevator, you've probably felt it before. When the elevator first takes off upward, at that point, it's actually going from 0 speed to some speed upward. So it's literally accelerating upward. And especially if your legs are really tired, you'll feel your whole body sort of squish down, because what happened was you started experiencing an apparent increase in weight. It wasn't really an apparent increase in weight, or it wasn't really an increase in weight. What it was an apparent one, because what happened is the scale has to hold up not only you, which has a weight of your mass times g, but it's also got to provide the force that accelerates you upward, like the elevator's doing. So you end up getting mg plus m times a, basically. And that's why the apparent weight increases when you're accelerating upward. Now, if you wait till you get near the top, and then all that time while you're passing numerous floors, you're moving at a constant velocity. So your apparent weight would just go back to your normal weight. But once you get near that floor that you're going to stop on, it's going to start to slow down. And then your momentum tends to keep you going upward. So the actual scale that's holding you up now holds mg minus that momentum that tends to keep you going up, and you get an apparent weight loss. The same thing, of course, happens when you accelerate downwards, which is what that is anyways, because slowing down on the way up is the same thing as speeding up on the way down. So those are apparent weights, but I'm going to do for a very specific problem, which is an inclined plane on an inclined plane. So let me draw this inclined plane so you'll have some idea what we're talking about. So I'm going to draw an inclined plane like that. Now I'm going to draw another inclined plane that is congruent to this one. In other words, it's more or less identical. What I'm going to do is imagine it's got these little frictionless wheels under it like that. Okay. And then on top of that, I'm going to put a scale. And then on top of that scale, I'm going to put me. And this is classic. My daughters used to always do this. Basically, whenever they drew me with exactly 5 hairs on the top of my head. So it kind of cracks me up, now that they're all grown up and living at college and all that good stuff. But anyways, there's me. Oh, wait a second. I forgot my big bicep. Oh yeah, big bicep. Okay. Anyways, now what's going to happen is this inclined plane with the scale on it is going to tend to accelerate downward. I'm going to treat this whole thing as frictionless. And I'm going to say my mass is m. And what I want to know is the apparent weight of, whoa, where's my, I don't even know where I put my phone. Oh, there it is. What I want to know is my apparent weight in this scenario. So it's going to take a little bit of time. Yep. All this time I've been trying to remember whether apparent has 1p or 2. That doesn't look right at all. I wonder what it says. Apparent. Yep, it's right. Arent. Okay, so apparent weight equals question mark. I'm going to call that quantity F sub S because it's the force that the scale does. So the first thing I got to figure out is when I draw a free body diagram for me, what I'm going to have is, this is a FBD for me on scale. Now, what I'm going to do is I'm going to draw the coordinate system like this. And all I really am going to care about in this case is what's happening in the y direction. And you'll see why in a second. So what I have here is a mass m. I have acting on that mass m a force due to the scale. I'm going to call this direction the positive y direction. I'll call this direction the positive x direction. Now, in addition to that, I have acting on me is the weight due to gravity. So that's just going to be mg like that. All right. Now, in the case of this thing going down the incline, what we have is an acceleration of negative a. Okay, it's going downward, and that's what I call my negative direction. So when I set up the summation of the forces in the y direction equals mass times acceleration in the y direction, what I end up getting is the force on the scale, which is in the positive direction, minus mg, and that's minus because it's plus a negative, and the negative is because it's pointing down. And that's all equal to negative MA. Remember, the A is downward, so I had to call it negative A. And what this tells me is that the force on the scale is equal to mg, or actually, I should say it this way. Yes. The mg definitely becomes positive over here, but here you go. Notice the MA is already there, so that's going to be minus MA. So ultimately, what this is going to be is M times G minus A. And now I need to calculate what that A is. So to calculate what that A is, I now need to go back and do the free body diagram for me on this incline. Okay. So now what I'm going to do is draw a coordinate system. We'll draw a coordinate system that has an x-axis, let's call it x prime that way, and a y prime axis that way. And I have a mass m that way. Now, what I know is the only forces acting on this are the normal force and, of course, my weight due to gravity is pulling straight down. In that case, that's mg. And of course, if this angle's theta, then this angle's theta. And as we showed before, so too is this angle theta. So in this case, what I'm going to get is this force right here is mg cosine theta. And this force right here is mg sine theta. Okay. Now, the summation of the forces in the y prime direction just allows us to determine the normal force. I don't know why I wrote that prime up there. So the summation of the forces in the y prime direction equals mass times acceleration in the y prime direction. That's not necessarily very helpful for us, okay? And in fact, that acceleration should be 0. And what I get from that is just n minus mg cosine theta is equal to 0. I'm going to call that equation 2, but it's not useful for us at all. Now I'm going to do the summation of the forces in the x prime direction is equal to mass times acceleration in the x prime direction, which is really the only acceleration. So I'm just going to call that a. Now, in this case, what I get is negative mg sine theta is equal to m times a. So you see that equation 3, a is equal to negative g sine theta, and that's along the x prime axis. Okay. So I need to get this related to the regular y axis. So need to find the component of a in the y direction. Because this equation over here, number 1, is done as if I know the y component. So I'll just say C equation 1. Okay. So what I have is this. I have an acceleration A is equal in magnitude to g sine theta. And what I need to do is put it in a component that is vertical. Remember, this angle right here is still theta. And in principle, I could also put it in a x direction, but that's the one that I don't really need. So this is my a sub y, which is what I want. This is my a sub x, which I don't need. So as I had told you, when you first start doing vectors, it's okay to take time and write sine theta equals and then cosine theta equals and then go about solving them. I'm going to do that for this particular problem. I'm going to say the sine of theta, according to that triangle, is equal to opposite over hypotenuse, which is AY over G sine theta. Similarly, even though I don't need it, cosine theta would be AX over g sine theta. I'm going to call this guy equation 4, and that's one we're going to use. I'll call this one 5 just because I don't feel right about not calling it something. Okay, so now I will solve for a sub y, and when I do that, I get a sub y is equal to g sine squared theta. Everybody see that? I will call this equation 4 prime. Now I'm going to plug 4 prime into 1. When I do that, I get the force due to the scale is actually m times g minus g sine squared theta, like that. Okay. Well, I can simplify that and say F scale is mg times 1 minus sine squared theta, like that. And that would also be equivalent to mg times cosine squared theta. So in fact, all of these are fair answers. So that's one version. And that's the other version. Anybody have any questions with that? So answer this. What do you think FS is for uh, the scale sitting on a horizontal surface? So in other words, you aren't talking about something sliding down an incline anymore. We're just saying, hey, what if we didn't have an incline? It was just sitting on a flat surface. What would you expect the reading of the scale to be? Anybody? What does a scale normally read?
Would it just be 0? Or
Uh, 0 is what would happen if the object was in free fall. So
okay.
like if I shifted that angle from theta to 90 degrees,
Mm-hmm.
then I would expect the object to be in free fall. And I've mentioned this a couple times to you before, but the reason astronauts in the International Space Station and stuff are weightless is not because there's no gravity up there, but because they're in free fall while they're orbiting around the Earth. That's sort of the definition of a circular orbit, is you're falling closer and closer to the center of the planet, but you don't get any closer because you move as much to the left or right, uh, so that when you move downward, you're not getting any closer. Okay.
Yeah.
Would the scale read your regular weight then? If
Yeah,
it's
that's
in
what I was shooting
Okay.
for. You'd expect it to read your regular weight. So I would say that infinity suggests it would be mg. Is that correct? So guess what? For theta equals 0 degrees, we get F sub s is equal to mg cosine squared 0 degrees, which is just mg. So yay, that worked out. this is an ongoing thing. When you solve a physics problem and you have some sense about what the answer should be in certain scenarios, you should check those scenarios. Now we're going to check for theta equals 90 degrees because Kayla was mentioning that. So when we get theta equals 90 degrees, we expect free fall. And free fall means weightless, so we'd expect 0. So let's see what happens. For theta equals 90 degrees, which again I say is free fall, Fs is equal to mg cosine 90 degrees squared, but the cosine of 90 is 0. So lo and behold, we get 0. So that's another check. Isn't that cool?
Yeah, thank you. That makes sense.
You're welcome. So everybody get that one? Y'all see how to do that now? Does that make some sense? All right. Now I've essentially completed everything that's necessary for chapter 4. I've even given you a little bit more than really is necessary by showing you that apparent weight problem. That's a much more quote unquote advanced type problem than is often solved. So I wanted to give you that and have a little bit more experience. Now I'm moving into chapter 5. So let's say consider the position vector r of t is equal to r times cosine 2 pi over t times t times I hat plus r sine 2 pi over t times lowercase t j hat. Now, what I would like you to do is I want you to imagine t being in seconds, x being in meters, and y being in meters, like this. And what I'd like you to do is notice the stuff to the left of the I hat. That's the x. Okay. So this part right here is the x that goes in there, whereas this part right here is the y that goes in here. What I'm asking you to do is fill this out for t equals 0. Notice when t equals 0, I get 2 pi times 0 over t, which is still 0. The cosine of 0 is 1. So I get r for the x. When I put t equals 0 in the y term, I get sine of 0, which of course is 0, times r, which is of course is also 0. And in case you guys are a little rusty on this, I highly recommend you committing these to memory for the rest of your life. Okay. So that's y equals sine of x. And that's y equals cosine of x. This is 2 pi. And this is 2 pi as well. Okay. So hopefully that'll help you as well. So now what I want you to do is I want you to continue this for, let's say, t over 4. I want you to try it again for t over 2. I want you to try it again for 3t over 4. And then I want you to try it again for, let's soup it up a little bit and let's say 7t over 8, and then one more at just t. Okay. So let's see if you guys can go ahead and compute what those values are. So I just showed you how to do t equals 0. Now all you're going to do is put in for little t, capital T over 4. Notice that the t in the top of the t over 4 will cancel out with the t in the bottom inside the argument of the trig function. So then you have 2 pi over 4. And of course, you can reduce that to pi over 2. So you now have r cosine pi over 2 for the x, and then r sine pi over 2 for the y. So can anybody tell me what x is and what y is on that?
So at pi over 2, x would be what, 0?
Yes, and that's t
And
over 2.
then
I think you just misspoke it,
oh
but
yeah,
yeah,
t
that's
over
right.
2, I'm sorry.
Good job.
And then y would be just equivalent to r.
Exactly. Anybody want to give t over 2 a try? I'll give you a hint. For t over 2, this part's 0. T over 2 is going to basically turn out to be the trig function operating on pi, just plain pi.
Would it just be R for X?
Close. It's, remember, if you look at the
Oh, it's
cosine graph,
negative,
there you
isn't
go.
it?
It's negative r. Yep.
One.
All right. What about 3t over 4? What's going to happen there is we're going to get 3 halves of pi. 3 pi over 2. Anybody get an X for that?
Gotten 0.
Exactly. And what about for Y?
Negative r.
Very good. Because the Y is the sign and you get -1. So this would be negative R. Very good. Now this one's a little more complicated. I think you can see that the 2 is going to cancel out with the 8 and leave a 4 in the bottom. So I'm going to get 7 pi over 4, which of course is 1 3/4 pi. So maybe that'll help you a little bit. But I think the big thing is to realize that at least the magnitude should be roughly like a 45-degree angle, basically. So maybe you guys come up with the square root of 2 over 2 times r, and the negative square root of 2 over 2 times r for the y. And then I think you're going to get r and 0 for t. Okay. Everybody sort of agree with that in some sense, at least? All right, so I'm going to draw what we just discovered. Like that. And let's draw this like this. Okay. So there's my x-axis. And there's my y-axis. Now, what we technically plotted was a vector. So those values R0 is an XY coordinate for the end of the vector. I'm going to assume our R is 4 squares. So it'll be there, it'll be there, it'll be there, and it'll be here like that. Okay, so the first thing I'm going to do is find that R of 0 is that guy. And then the second thing I'm going to find is that R of t over 4 is that guy. Okay. Then R of t over 2 is going to be that one. Okay. And R of 3t over 4. Whoa, no. Is going to be that one. And then if you really wanted to try, what you'd see is roughly right here would be R of 7t over 8, like that. And this is also t equal the period. Okay. So the ends of these arrows are actually pointing out exactly where the particle would be at various times. So in principle, what I'm trying to do is show that that vector field that I just did, in fact, made a circular path. And you can see that it started off on the positive x-axis and went around counterclockwise. So I'm going to say it's going this way. Okay. Now, what I'd like you to do is I'd like to see you guys compute v of t, which, by the way, is dr over dt, which we can write as d by dt. Remember, the shortest way to write a vector is to put it in the less than and greater than symbols. So I'm going to make this a little easier by calling this r cosine omega t, because the omega is a lot less to right than 2 pi over t, and it turns out that omega is exactly the right answer. So omega is defined to be 2 pi over t, and it's called the angular speed / frequency. Okay. And then the y component, of course, is r sine omega t. So now your job would be to say r times d by dt of cosine omega t, but you got to remember to use the chain rule. And this one will become r d by dt of sine omega t. But again, you've got to use the chain rule. So can anybody tell me what the x component is going to be? Don't worry, we're actually doing something intentional here. It's a derivation that your book does, but the way they do it, I don't find it that compelling. Whereas I find this way something the students can grasp a little bit. So can anybody tell me what the derivative of cosine omega t is?
Wouldn't it be negative sine omega t times then the inside of the angle. So would that be, I was trying to think of how to word the inside of the angle, but
Yeah, so you're going to take the derivative of the argument of the cosine, and the argument of the cosine or the sine is omega t. So the derivative of omega t with respect to t is just omega. So yeah, you're absolutely right. This is going to become negative r omega, now sine omega t. I think that's what you were trying to say. Yes, Kayla?
yeah, that's right.
Okay. Now, someone want to give the y component a try? I'm going to write it down, see if you guys can get it as well. Okay. So that is the actual velocity as a function of time. Is v of t a constant? Anybody have a guess on that? Do you think the velocity is constant that this thing is traveling at? We know at t equals 0, it was at r0, and then at t equals t over 4, it was at 0r. So we clearly can see that it's moving. But is its velocity changing as a function of time? So what I want to know is, let's calculate v magnitude of t, which is equal to, remember, this is just a two-dimensional vector, so we just use the two-dimensional version of Pythagorean theorem on it. Both term has a r omega, so you know it's going to have a r squared omega squared in it. I'm going to go ahead and head that off and realizes that it's going to be in both terms, so I'm just going to go ahead and factor it out. And then what I have left is the negative of sine omega t, but that will be squared, and negative sine omega t times negative sine omega t is positive sine squared omega t. And similarly, cosine squared of omega t becomes cosine squared omega t. And in fact, that is, I'll make this a square bracket to make some sense of it. So you see, that's what happens. But what is sine squared plus omega plus cosine squared?
1.
Right? And what is the square root of r squared omega? Squared. Excuse me.
Would it just be RW, or technically plus or minus RW?
Yeah, it's the principal square root since we're taking a magnitude of a vector. So yeah, it's r omega. So what we found is that v is equal to r omega, and it is equal to a constant. It's a constant vector, but it's a constant. Okay. So the magnitude's constant, but the direction is changing. So what we have discovered is, not only is this r of t that I gave you, not only is that the position vector for an object going in a circle, it's obviously the position vector for an object going in a circle with a constant velocity v. So now what I want you to do is calculate the acceleration. So a of t is dv over dt. This time I want you guys to calculate this. You calculate it, I'll calculate it. We'll compare our answers at the end. And we're also going to, of course, figure out whether it's a constant as well or whether its magnitude's a constant. Okay. Did you guys get the same thing for the acceleration being negative r omega squared cosine omega t, negative r omega squared sine omega t? Okay, so what we see is, in fact, the acceleration is a constant as well, because this quantity under the square root is just 1 again, and we get a is equal to r omega squared. So a is equal to r omega squared, but V equals R omega implies omega is equal to V over R. So A is actually going to be equal to V squared over R. And that's the big derivation I was trying to do. This is called centripetal. So that's center seeking acceleration. Now notice the r omega squared has a negative in front of it when we took the derivative. So I have negative r omega squared cosine omega t. If you put the r with the cosine omega t, what you see is the x component is the exact same thing as the x component of r, except multiplied by negative omega squared. And if you look at the y component, you'd see the same thing. It's the y component of r, but multiplied by negative squared. So what we can do with this is we can say, wait a second, this is kind of a big deal. What we just discovered is that the acceleration at that point points radially inward. At that point points radially inward. At that point points radially inward. And at that point, it points radially inward. And with this point as well, it points radially inward. So what you're seeing is this is truly the centripetal acceleration. And what we've just discovered is that if you wish to go in a circle of fixed radius, you can do so by going at a constant speed, and that speed is equal to V equals R times omega, where omega is 2 pi over the period, and the period is the time it takes to make one complete loop. If you do that, yes, you will have a constant speed, and you will have to maintain a constant acceleration that points radially inward, and that acceleration is V squared over R. Okay. So if you ever have to solve a problem where you need something to be going in a circle, then the right-hand side of Newton's second law, F equals ma, the A is going to be V squared over R. And then you got to make sure the left-hand side, which is the summation of the forces, is going to keep up with that. So we'll solve some problems with that next time. We only got about 5 minutes, but I wanted to show you one other thing so you can get started on chapter 5. So remember, this all is chapter 5. Now, what I need you to know about chapter 5 is there's two types of friction that we're going to study. One of them is F static, which we're going to call just plain FS, okay? And what I mean by that is if, for instance, this calculator is laying on the back of my hand, if the calculator is not moving with respect to my hand, then the friction force is called a static friction force. And what you'll see is if I push on it with 1/1,000,000th of a Newton, it doesn't budge. If I push on it again, but this time with 2/1,000,000ths of a Newton, it still doesn't budge. If I keep doing that, it will keep not budging so that the friction force continues to supply just enough force to stop it from moving. But there is a limit, and that limit is, in fact, given by less than or equal to the coefficient of static friction, that's what the mu s is called, times the normal force. This is called the coefficient of static friction. And there's a table of values right in your book. So for instance, there's a static friction for rubber on concrete. There would be a different one for rubber on asphalt. There'd be a different one for plastic on wood. There'd be a different one for wood on wood, and so on and so forth. And you can just look that up. But the way static friction works is static friction gives as much as it can up to mu static times the normal force. Then when you reach mu static times the normal force, that's just enough to allow it to start moving on the back of my hand. But the neat thing is, try this yourself. Lay something that's got some grip to it so it won't just slide easily. Lay that on your table or your desk and give it a little push. And notice if you push just a little bit harder, it still doesn't move. A little bit harder, it still doesn't move. But eventually you push it hard enough, not only will it move, but then it gets a lot easier to push. That's a key physical principle. The key physical principle is this. Key physical principle is that F static is greater than F, and this word is kinetic. And that means the friction that happens as this thing is sliding across like that. Now, the friction kinetic is equal to mu kinetic times the normal force. Okay, so notice this one's exactly equal, whereas the other one was less than or equal to. So this is really all you need to complete essentially everything from chapter 5. I want to give you more examples, and I will give you more examples next time, but I wanted to give you enough to be able to start on your homework. Remember, you all have a actual test due Sunday. That's an online test. You will get a 0 if you don't do it. Okay. I've already had to give a bunch of people an extension and given them another chance to take the first test. I'm not doing it again, so make sure you guys do that. This should allow you, like I said, good enough to get started into chapter 5. I would say if you're somewhat adept at reading your textbook and following the examples, you could probably do all of chapter 5 with what I've seen, what I've shown you. But the main thing is we're going to not require you to do that because I'm going to give you some more examples. Now, time is up and you guys are free to go, but I will tell you that this static friction being larger than the kinetic friction. Oh yeah, make sure you text or you chat me your first and last name for roll. But what I was saying was the fact that the static friction is greater than the kinetic friction is exactly why we turn into a skid when snow time comes or when it's raining. So for instance, if you're driving down the road and you're going to the left over a curve, what inevitably happens is if it's on a snowy surface, the tail end of your car might swing out to the right, even though you're trying to turn left. Well, what you're supposed to do is turn into the skid. So since your tail is swinging out to the right, you want to rotate your steering wheel to the right. And what's happening there is your car is trying to slide sideways. But if you turn your wheel this way, there's a small chance that you caught it early enough that your tires will just align with the direction it's trying to slide. And by aligning with the direction they're trying to slide, they can reestablish kinetic friction, or excuse me, reestablish static friction instead of kinetic friction. And that will actually keep you out of the skids strictly because the static friction is bigger. Okay. You guys are free to go. Don't forget to do your test, please. Don't forget to text or to chat me your first and last name for roll. And thank you everybody for coming. And I'll wait for the last person to leave in case anybody has any questions.
Thank you. Have a good one.
Thank you too, Jacob.
Hey, I had a quick question. I sent you over an email because my car broke down this morning and I'm normally coming into your the noon lecture.
Right.
So I don't know if I could still get how that will impact attendance, but I at least wanted to jump on and just not miss out on what we did in class today. So I
You
didn't
did
know.
this, we did the exact same lecture that I just did here.
Okay, so would I still be able to like send over my name in the chat for attendance purposes, or should I just?
Oh, yeah, the attendance won't matter. The lab matters. But
Okay.
if you only miss one, it's only 1 point off. So it's not that big a deal. And we don't have a difference between excused and unexcused absences. The downside is that you did miss the lab. Oh, no, you didn't, because you're the 241 class. So you didn't miss the lab. So yeah, nothing's going to hurt you here.
Okay, thank you.
You're welcome. See you, Kayla. Hello, Hannah. The other person that's, or actually, is this Hannah R or is this the other Hannah?
This is Hannah Keen. My Wi-Fi has been funny today, so I had to get it on with my phone. That's why my camera was off.
Oh, gotcha.
I wanted to make sure because you had said something about at the end about the test. It's just the online test, right? That's due February 18th on Sunday.
Yes, February 18th
Okay.
at 11:59 p.m. And you get, I think I set up to 3 attempts. Sometimes I'll do 4 or 5, but you get at least 3.
Okay, perfect. And then I wanted to thank you because I am actually getting through some of the homeworks now. I was actually able to finish chapter 4.
All right.
And I started back and I'm working through chapter 1. So
Cool.
my goal is to have chapter 1 and 2 done before Sunday and then 3 and 4 by next week. So
That's cool. And you'd be
thank you.
surprised how much you're going to know about 1 and 2 just from doing 3 and 4. So you'll be a lot better off than you think. Good job, Hannah.
Awesome. Okay, thank you. I'll
Keep
see
it
you on
up.
Monday.
See you then. Thanks for coming.
Yes.
Bye, everybody.